times 50 squared. All you're going to do now is you're going to multiply the numbers. Please don't forget to square that velocity, and work equals blank joules. Don't forget, though, kinetic energy has an SI unit of a joule. Work has an SI unit of a joule. Now, a bullet that has a mass of 20 grams, that's the mass, but is grams an okay value? No, it's not. We'll come back to that in a minute. Was shot with a velocity of 800 meters per second, hits an oak tree and sticks inside of it to a distance of 0.04 meters inside of the oak tree. What is the average force, question mark F, that the bullet hit the tree with? Well, work equals force times distance. Okay, I'm looking for force. I have distance, but I don't have a work number. So I can go ahead and say work equals KE. And I can derive, or I can change this up. And I can go ahead and manipulate how I need to. Force is my unknown value. The distance is 0.04 meters, 1/2. The problem is the mass is in grams, so let's go ahead and do that over here first. King Henry drinks utterly delicious chocolate milk. I'm going from grams, which is right here, the base unit, to kilograms. So that means I need to go 1, 2, 3 places to the left. 1, 2, 3. So my new number is 0.02 kilograms times a velocity of 800 meters per second square. Don't forget to square that number. Let's go ahead and isolate for the force by dividing by 0.04. Cancel. Divide by 0.04. Force equals blank newtons. Go ahead and finish up the math. Not too bad, I think. I think we're doing good. We're kind of coming to a closing part where we're almost done now. Now, next part here says that mechanical energy is energy that is possessed by an object due to its motion or due to its position. Mechanical energy can be either KE, which is energy in motion, or PE, which is stored energy. For an example, a moving baseball possesses mechanical energy due to both of its high speed, which is kinetic energy, and its vertical position above the ground, which is its potential energy or gravitational potential energy. So since we know that, one more time, mechanical energy is energy of either motion or position or both, then that becomes our new equation, or another equation that we're going to talk about. The conservation of mechanical energy equation states that as an object changes its position, its speed and motion also changes. Energy is not lost at all, but instead it is transformed into different types of energy. Remember, the law of conservation of energy states that it cannot be created or destroyed. Okay? So our equation here is what we call the TME. Now, TME stands for total mechanical energy. So the equation states total mechanical energy equals the PE plus the KE combined. And Since energy cannot be created or destroyed, then the total amount of energy in the beginning of a system should equal the total amount of energy at the end in any other position or location within the system. So now this TME can be changed into KE initial plus PE initial equals KE final plus PE final. Just stating that however much energy I have over here at every location of the system should be the same mechanical energy number, not the same potential or kinetic energy, because potential and kinetic energy can change due to its position and speed and location. Okay? But the total mechanical energy will be the same at every given point. So let's take a look at a couple of examples here, and then we have a couple of examples, workout problems, and then we are done with our notes here. Okay, so let's go ahead and take a look at this next part right here. Put it into a math equation now. We're looking at it mathematically. Let's do that. We have a diagram over here, and in this diagram, it has somebody who's skiing. At the top of the ski ramp, they show me that the kinetic energy is 0 and the potential energy is 50,000 joules. What I do know from both of those combined is when I add them together, it equals the mechanical energy. So 0 plus 50,000 equals 50,000 joules of mechanical energy. So that means that every single location, this skier should have 50,000 joules of mechanical energy, which is the combination of kinetic and potential added together at any given location. But again, we're talking about a closed system, okay? Don't forget that. We're going to assume that all of our systems are going to be closed. In real life, they're not, but we're going to assume that they are. Next one. Is the total amount of energy at the beginning of the skier's run equal to the total amount of energy at the end? Yes, it is. 50,000. 50,000? 50,000. What happens to the potential energy as a skier goes down the slope? 50, 30, 15. What happens is that it decreases. Right? It's decreasing. Was the energy destroyed? No, it was not. If not, what form of energy is it taking as it's going through the run? So the PE transforms to KE. Okay? But the total ME, which is the mechanical energy, is the same at any given location. Using the picture below with the pendulum, fill in the missing energy or energies of position 1 and 4 here. Now, when we talk about a pendulum that's hanging from the ceiling or hanging from something, that's a little different. When they pull the pendulum back, okay, to start, at that starting position is considered to be the highest position. Okay? Now, before it starts, they're holding it. What is the velocity? 0. So in the beginning, before it starts, the kinetic energy is 0 joules, and the potential energy, they told me, is 6 joules. When they release this pendulum, it's going to start to rotate and move this way, and then it goes back, and then back, and it's going to keep doing that over and over and over, right? Now, at position 2, if they told me that I have 3 joules of kinetic energy, and I know that the ME at position 1 is 6 joules, then at this location, the ME better be 6 joules. And at this location, the ME better be 6 joules. And at this location, the ME better equal 6 joules. Now, don't forget, the kinetic and potential energy is going to change because of energy transformation is occurring. Now, if there's 3 joules here, then there's 3 joules of energy for potential energy because that equals 6. Now, at position 3, which is over here at the, let me say this, bottom, then at the bottom, look at this bottom, the PE is 0, and all of the ME is being transformed into KE. This is considered to be the bottom, the lowest point. So in that case, the PE is 0 joules at the bottom, and all of it must be KE because it has to equal 6 joules of ME. And when we go back over here to number 4, which is back at the top, again, at the top, what happens? It actually, just like an object, when we were talking about kinematics last semester, when we toss an object up, it literally stopped for a split hair of a second, and then it changed directions and started to go back down. The same thing here. Yes, it's attached or tied to a piece of string, but at the top, when it came over here to this position, it stopped for a split hair second, turned around, and changed directions backwards. So at that point, the KE is 0 because it stopped, and all of the ME is put into PE, which is 6 joules. Not bad. It's pretty easy. It's adding and subtracting. I'm going to let you do those two over here. They're not bad at all. They're pretty easy. Let's do the next one down here. At the start, which is also the top, my KE is going to be 0 joules. All of my ME is put into, that should say PE, or potential energy, of 300 joules. But look at this. At the bottom, I have 0 PE. All of my ME is put into KE, which is 300 joules. But if I'm halfway right here, at the halfway location, that means I have half of it as PE and I have half of it as KE. Let's look at a couple of problems so we can practice it. The main problems here that are going to be a little confusing is going to be probably the work energy theorem equations. But let's see what we do have. What will the kinetic energy of an arrow having the potential energy of 50 joules just after it's shot from a bow? So right before the bow and arrow is released, that bow and arrow at the position of right before it's released has 50 joules of PE. And obviously it's going to have 0 joules of KE. And I know that the mechanical energy, or ME, is the total of them combined. So the moment that it's released or shot, now the potential energy is being transformed to the kinetic energy. So my KE now is going to be 50 joules of energy. A boulder is raised above the ground so that its potential energy is relative to the ground is 20,000 joules. It is then dropped. What is the kinetic energy just before it hits the ground? So there's this boulder, and it's about to fall. Right at that split second of just almost impact, what is the kinetic energy? Well, at this location at the top, if its PE is 20,000, then its KE must equal 0. So at the bottom, its PE must equal 0, and its KE must equal 20,000, because I know that the TME is the total energy, which is the same at every given location for that system. 20,000 is the answer. Let's keep going. A 500 kilogram, okay, that's a good number, it's in kilograms, car is moving at a velocity of 28 meters per second. The driver sees a barrier ahead. If the car takes 95 meters to come to rest distance, what is the magnitude of the average force, (F), necessary to stop the car? Well, I know that if I'm going to answer force for this unit, work equals force times distance. I don't have a work number, so I can't do that. So what I can do, though, is that I can say that work equals kinetic energy, and I can derive and change it to say FD equals 1/2 mv squared. We're looking for force times the distance of 95 equals, change the fraction to a decimal. The mass is 500, which is kilograms, a good value. And the velocity is 28, but please don't forget to square the velocity number only. Divide by 95, cancel. Divide by 95, the force equals blank newtons. I know you can do that. Let's go to the next question. A bullet with a kinetic energy of 400 joules, that's the KE number, strikes a wooden block where a resistive force of 8 times 10 to the third, that should be third newtons. That's my force number. Stops the bullet. What is the penetration of that bullet into the block? Question mark. What is the distance that it moved into the block? Well, KE is 1/2 mv squared, and they didn't give me anything for velocity, so that's not going to cut it. And then they gave me a force number, and they're asking about distance. So I can say that KE equals work, and I can change the equation to say 1/2 mv squared equals force times distance. And let's go ahead and let's keep working that out. 0.5 equals the mass of, I don't have it, times the velocity of, I don't have that either, equals force times, well, I do have that, 8 times 3 to the times 10 to the third power times distance, and I don't know it. But do you see what we did not have to do here? In this case, I changed it to the whole equation for kinetic energy over here, but I didn't need to do that because they gave me the KE number. And so the KE number is actually 400 already, and I know it. Now we can solve for distance by dividing by 8 times 10 to the third power. Divide by 8 times 10 to the third power. The distance equals blank meters. A couple more problems and we're about done. I just want to make sure that we got these work kinetic energy equations. A 75 kilogram bobsled, that's the mass, is pushed along a horizontal surface by 2 athletes. After the bobsled is pushed for a distance of 4.5 meters, which is a good number, starting from rest, if its speed now has a velocity of 6 meters per second, find the magnitude of the force, question mark F, on the bobsled. Well, work equals force times distance. I'm not going to be able to use that number, so I'm going to have to change it to say work equals kinetic energy. They didn't give me the kinetic energy number, so I am going to have to break this apart to say F times D equals 1/2 mv squared. Now I'm looking for force. I know the distance is 4.5 equals, let's change the fraction to a decimal, 0.5. The mass is 75 kilograms, which is a good SI unit. Don't change it. And the velocity is 6, but please don't forget to square that 6. Divide by 4.5, cancel it. Divide by 4.5. The force comes out to blank newtons. Finish that up. The last one says that a student is wearing a frictionless roller skates on a horizontal surface and is pushed by her friend with a constant force of, 45 newtons. So they gave me the force number. How far, question mark distance, did the student was pushed so that her final kinetic energy came out to 352. Well, if I'm talking about kinetic energy, I know that's 1/2 mv squared, but I don't have no mass or velocity. Okay, so I'm going to have to change this to say KE equals work. And I can go ahead and change this up if I need to a little bit. Let's change this to 1/2 mv squared equals F times D. But look at this. I changed the KE, but they gave me the KE value. So let's go ahead and put that in here. 352 equals the force of 45 newtons times the distance I don't know. Divide by 45, cancel that out. Divide by 45. Distance equals blank meters. Not too bad, I think. So we just went over all these questions together. There's only a couple of questions on the notes that you do need to practice, and they were fairly easy and simple. I know you can do them. All of those questions that I worked out for you and left blank, or this one, you need to do them or you're going to start losing a point for every single one that's missing, okay? So now we've covered all of the notes now for this unit. That means that we're prepared to take the next quiz that will be online. And then we do have a test, but we still have a couple of weeks till then. So we should be okay till we take the test. In class this week, we are going to finish talking about the rest of our notes. And we have a few more things to do as well. Have a great day. Bye-bye.